The next afternoon, the upstairs classroom smelled faintly of cookies, pencils, and dry erase markers.
I support any chemistry lesson that begins with snacks.
Only if the recipe works. This card says 2 cups on one line and 1 cup later. That is not balanced.
Good. Today, balance is not about looking neat. It means the count is correct.
Chemistry has recipes too. We call them chemical equations.
Do chemical recipes also become suspicious when the numbers do not match?
Suspicion level academically appropriate.
Exactly. In a chemical equation, the reactants are the starting materials and the products are what they become.
So the equation has to keep track of what goes in and what comes out.
Yes, but we do not balance it by guessing. We count atoms.
That sounds stricter than baking. Cookies forgive me sometimes.
Atoms do not forgive bad accounting.
Theo placed colored atom tokens beside a blank equation card. Mabel 7 opened a table with 2 columns, reactants and products.
Ready to count each atom type separately.
I will treat every atom like a tiny ingredient with strong legal rights.
Perfect. Our question today is simple. How do we write a reaction without losing atoms?
Theo turned over a clean card and wrote the first chemical recipe of the afternoon.
Here is our starting equation. H2 plus O2 produces H2O.
The left side shows the reactants. Reactants have the substances we start with.
So reactants are like ingredients before the recipe changes them.
Exactly. The arrow means produces or yields. It tells us what the reactants become.
The arrow is not decorative, it is a very serious little direction sign.
On the right side, we have the product, water, written as H2O.
Honestly, it looks finished, short, clean, confident. Very respectable handwriting.
Visual neatness does not equal chemical balance.
So even if the sentence looks complete, the atom count may still be wrong.
That's the point. A chemical equation is not balanced because it looks nice.
It is balanced only when the number of each atom matches on both sides.
So chemistry is basically asking, did everyone who entered the story come out somewhere?
I support atom attendance.
Mabel 7 drew 2 columns under the equation, reactants and products.
Next, we count. Does this equation actually keep every atom?
Mabel 7 drew a clean table under Theo's equation, with reactants on the left and products on the right.
Beginning atom count procedure. We count each type of atom separately.
On the reactant side, H2 has 2 hydrogen atoms.
And O2 has 2 oxygen atoms.
Reactant side, hydrogen equals 2, oxygen equals 2.
Now count the product side. The product is H2O.
H2O contains 2 hydrogen atoms and 1 oxygen atom.
Product side, hydrogen equals 2, oxygen equals 1.
So hydrogen is fine, but oxygen is acting like it forgot to arrive.
The left side has 2 oxygen atoms. The right side has only 1.
Exactly. The equation is not balanced yet.
That does not mean the reaction is impossible. It means our written model is incomplete.
Conclusion. Visual neatness failed the atom count test.
The equation looked calm, but the oxygen column was quietly dramatic.
The class stared at the table. The problem was no longer hidden in the symbols.
Next, we need to fix the equation without changing what the substances are.
Pip raised one hand very carefully, as if the equation might hear him.
Could we simply change H2O into H2O2O2 so oxygen feels included?
That is a very common mistake, and it is exactly why this lesson matters.
H2O and H2O2 are not the same formula.
So changing the little number changes the substance, not just the balance.
Subscript detected. It belongs inside the chemical formula.
Right? A subscript tells how many atoms are inside one molecule.
So we are not allowed to edit the molecule just because our table is annoyed.
Correct. If we change a subscript, we are talking about a different substance.
The tiny number has more authority than expected.
Exactly. To balance an equation, we do not change subscripts.
Then what can we change?
We change coefficients. A coefficient tells how many molecules or groups we have.
Coefficient, outside the formula. Subscript, inside the formula.
Outside number changes the crowd. Inside number changes the person.
Theo placed a blank coefficient card in front of the equation.
Next, we use coefficients to balance the equation without changing the formulas.
Theo slid 3 blank number cards across the table like tiny stage directions for molecules.
A coefficient is a number in front of a formula.
It tells us how many molecules or groups we have.
So if the formula is a recipe for one molecule, the coefficient says how many servings.
Coefficient equals molecule crowd size. That is socially useful.
Example 2H2 means 2 molecules of hydrogen.
Right. The formula H2 stays the same. The coefficient changes how many H2 molecules we are counting.
So outside number changes the crowd. Inside number changes the person. I am keeping that.
Good. That sentence is not fancy, but it is accurate.
Can we use coefficients to fix the oxygen mismatch from the last page?
Yes. We need to add molecules, not edit molecules.
Current equation, H2 plus O2 produces H2O. Oxygen count does not match.
Requesting responsible molecule crowd adjustment.
Exactly. We will place coefficients where they make the atom counts match.
The blank number cards weighted in front of the equation.
Next, we balance the equation by changing how many molecules we have.
Theo placed at number 2 in front of H2O on the product side.
If we write 2H2O, we have 2 water molecules.
Product side check. 2 water molecules contain 4 hydrogen atoms and 2 oxygen atoms.
Oxygen is fixed, but now hydrogen is too high on the product side.
Good catch. Balancing one atom can change the count for another atom.
So we place a 2 in front of H2 on the reactant side.
Now we have 2 groups of H2. Hydrogen crowd expanded responsibly.
Reactant side, 2H2 gives 4 hydrogen atoms. O2 gives 2 oxygen atoms.
And the product side has 4 hydrogen atoms and 2 oxygen atoms.
So both sides match now, hydrogen 4 and oxygen 2.
Exactly. The balanced equation is 2H2 plus O2 produces 2H2O.
In symbols, 2H2 plus O2 arrow 2H2O.
Atom conservation confirmed.
All atoms have checked in and checked out.
The equation no longer just looked tidy, it counted correctly.
That is what balance means in chemistry. Each type of atom matches on both sides.
Sera tapped the arrow in the balanced equation, not the numbers.
The arrow matters because it separates what we start with from what we make.
On the left, 2H2 plus O2 are the reactants.
On the right, 2H2O is the product.
Balanced equation, 2H2 plus O2 produces 2H2O.
So the arrow is basically saying before on this side, after on that side.
Yes, but say it academically, the reactants produce the products.
I can do academic. The reactants produce the products while everyone keeps their atoms.
Good. A balanced equation is also a sentence.
It tells what substances react and what substances form.
Exactly. We can read it as hydrogen and oxygen react to form water.
Coefficient language, 2 molecules of hydrogen react with 1 molecule of oxygen.
And they produce 2 molecules of water. Very tidy attendance.
The class practiced saying the equation out loud until it sounded less like symbols and more like science.
Next, we check every claim by counting before we believe it.
Ben leaned closer to the board, dangerously confident for a person near chemistry.
If an equation looks short and symmetrical, may I trust it emotionally?
Absolutely not. That sounds like how furniture gets stuck in stairwells.
Correct answer. Count before you claim.
Here's a new-looking equation. N2 plus H2 produces NH3.
It has excellent handwriting. I am already suspicious.
Beginning atom count table. Reactants, nitrogen equals 2, hydrogen equals 2.
Product side, NH3 has 1 nitrogen and 3 hydrogen atoms.
So both columns are wrong. That is efficient failure.
Exactly. The equation is not balanced yet, even though it looks tidy.
First count, then choose coefficients.
Do not claim balance until each atom type matches on both sides.
The table is the lie detector for neat equations.
Mabel 7 highlighted bold mismatches, and the class did not try to fix them too quickly.
That habit matters. In chemistry, a balanced-looking equation still has to pass the count.
Mabel 7 left the new equation on the board and opened a fresh row in the atom count table.
Current equation, N2 plus H2 produces NH3. Status, not balanced.
Start with nitrogen. The reactant side has 2 nitrogen atoms.
The product side has 1 nitrogen atom, so place a 2 in front of NH3.
Product update, 2 NH3 gives 2 nitrogen atoms and 6 hydrogen atoms.
Nitrogen matches now, but hydrogen became too high on the product side.
So we place a 3 in front of H2 on the reactant side.
3 groups of H2. That is 6 hydrogen atoms arriving in pairs.
Reactant side, N2 gives 2 nitrogen atoms. 3H2 gives 6 hydrogen atoms.
Product side, 2NH3 gives 2 nitrogen atoms and 6 hydrogen atoms.
Now the atom counts match. The equation is balanced.
In symbols, N2 plus 3H2 produces 2 and H3.
So the coefficients are 1, 3, and 2.
The numbers are uneven, but the atoms are not.
That made Ben squint at the equation with fresh suspicion.
Exactly. Balance does not mean the coefficients look the same. It means the atom counts match.
Ben pointed at the balanced equation as if it had personally offended symmetry.
Wait, the coefficients are 1, 3, and 2. That does not look balanced.
It looks lopsided, but the atom counts match.
That is the key. Balance does not mean equal coefficients.
Coefficients are tools for making atom counts match.
N2 plus 3H2 produces 2NH3. Nitrogen 2 equals 2. Hydrogen 6 equals 6.
The coefficient 1 is usually invisible. We do not write it in front of N2.
Invisible one is doing quiet paperwork.
And the 3 in front of H2 does a different job from the 2 in front of NH3.
So we should not force every coefficient to be the same number.
Right. We choose coefficients that protect every atom type.
Final test. Compare each element, not each coefficient.
So chemistry is not judging the equation by outfit symmetry. Rude, but fair.
The class wrote one careful sentence under the table. Balanced means equal atoms, not equal coefficients.
Next, we practice saying that sentence in precise scientific English.
Sera turned the balanced equation into a sentence frame.
Try this. The equation is balanced because each side contains the same number of each atom type.
For our ammonia equation, each side contains 2 nitrogen atoms and 6 hydrogen atoms, and 100 atoms.
So the complete sentence is, the equation is balanced because each side contains 2 nitrogen atoms and 6 hydrogen atoms.
Excellent. That is precise scientific English.
Sentence frame saves the equation is balanced because blank.
I enjoy a blank that demands evidence.
Can my blank say, because Mabel 7 said so?
Tempting, but no. The blank needs counts.
We can also explain coefficients. The coefficient 3 in 3H2 means 3 hydrogen molecules.
And the subscript 2 in H2 means 2 hydrogen atoms inside each molecule.
Good. Coefficient outside, subscript inside, different meanings.
Recommended wording. Coefficient tells how many groups. Subscript tells how many atoms in one group.
That sentence has excellent posture.
By the end, the board looked less like a puzzle and more like a paragraph with evidence.
When your chemistry sentence includes the count, your reader can check your reasoning.
The afternoon light moved across the upstairs classroom, catching the colored atom tokens on the table.
So what does a balanced chemical equation prove?
It proves our written model keeps track of every atom.
The atoms can rearrange into new substances, but they are not lost.
Conservation of atoms confirmed by matching counts on both sides.
No atom vanishes. No atom sneaks into the room late with a tiny hat.
Honestly, that is stricter than most group projects.
It is strict because chemistry has to describe matter accurately.
Reactants become products, but the atom count stays conserved.
So balancing is not decoration. It is evidence that the model respects conservation.
Final rule. Do not change subscripts. Use coefficients. Count each atom type.
Atom attendance forever.
Sera erased the board slowly, leaving only the final balance equation for a moment longer.
Next time, those coefficients will tell us something even bigger, reaction ratios.
If ratios involve snacks, I am emotionally prepared.
Good. Bring that energy to the next chemistry story.